Hey everybody, so we're going to be talking about similarity transformations today. So I want to remind you that with similarity transformations, they're keeping things proportional. Pretty much similarity transformations are just dilations. So what we were talking about in transformations in that chapter. So here's a reminder, okay, that this is our scale factor of 2.5, meaning we multiplied it, right? And here's some info right here about dilation. It's there for you to read if you need it, but we're going to keep going. All right. This word is new for you guys, invariant point. That's a point that maps onto itself. Pretty much when you apply a dilation or any transformation, it ends up becoming that same point it originally was. So that's kind of a cool little side note. Usually that can be something like 0, 0, the origin, but it can also be different points from time to time. All right, your dilations. Remember, for a dilation centered on the origin, we use the algebraic representation xy goes to kx, ky, and remember that k is equal to my scale factor, or my multiplier. All right, if I am enlarging something, my k value, or the absolute value of it, in this case, is going to be greater than 1. It's an enlargement. It's larger than 1, which means anything between 0 and 1 is going to be less than, or it's going to be a reduction right here. All right, some quick notes. Scale factor is the ratio of the corresponding sides of similar polygons. All right, and the scale factor of dilation, which is what we're going to be talking about, technically they're the same thing, but scale factor can be used in more everyday speak. Now, scale factor of dilation is a number that you have to remember multiply the pre-image by to get your image. It's the multiplier. Think about it. You multiply factors to get your final answer. All right, so we are going to talk about scale factor. Remember that order does matter, and we were talking new to old. In this case, I've given you where it's going to be anyways. New to old is already set up. The way we wrote it last time was k equals new over old. It's the same thing, and I'm going to write it primarily in fractions. If you do end up writing your answer as something like this, that's fine. You should be able to let it through. But commonly accepted is more the fraction, so I would recommend that. Now, the scale factor of ABC to DEF. So we can set up an extended proportion of ABC to DEF, and notice it's going this way, to DEF, which is going that way. We can see that by the 1, 2, 3 congruency marks on the angles. So we've got 8 to 12, 10 to 15, and then 14 to 21. Now, if you set them equal to each other, it will be a true statement because all of them end up equaling and simplifying to 2 over 3, which is going to be our scale factor or our k value. All right? I put that equals k so you remember that that's our scale factor, and that's what we were looking for. When I'm asking you for the scale factor, you're just typing in the number 2/3. If it is something that you can simplify into more exact terms, like 1/2 can be simplified to 0.5, then you would just write 0.5 or 1/2, either or. All right, scale factor of DEF to ABC. Well, looking at the one right before it, we know we can just use one of them and do 12 over 8. And we know it's just going to be the reciprocal of what we got in the first one. And it's just going to be 3 over 2. That easy. Now, what is the ratio of the perimeter of triangle DEF to triangle ABC? Okay, well, let's find the perimeter of ABC. Remember, perimeter is found by adding all the lengths of the sides together. So 8 plus 10 plus 14, which ends up getting you 32. And if we find the perimeter of DEF and add up all three of those numbers, you get 48. So you have 48 to 32. When you end up simplifying 48 to 32, it actually ends up simplifying to 3 over 2, which was the same scale factor that we were working with. So that is super important to note, because if you know the scale factor, and I've given you the perimeter of only one shape, then you could figure out the perimeter of the other shape. All right, if there is a dilation that maps triangle ABC to EFG, then they're going to be similar. We have to figure out if these are similar or not. The first thing you need to check if they have congruent corresponding angles. So what I'm going to do is find the slope of each side length. So I've got AB, BC, and then CA, and this is just the slope. And then those intersecting lines, if they've got corresponding intersections, then they have the same angle. So the slope of AB is negative 1 over 2. The slope of BC is 2 over 1. And yes, we can simplify that to 2, but for this case, we're just going to leave it here, so it makes our life easier. CA is 1 over 3. All right, now let's find it for EF, FG, and GE. And if it helps you to color coordinate, here's the blue triangle, and here's the orange triangle. All right, if you do EF, then you end up getting, negative 3 over 6, which simplifies to negative 1/2. FG, or GF, right there, that ends up going to 6 over 3, so that's 2 over 1. And then GE gets us and well, actually, GE, yeah. I think I've got this backwards real quick. So EF down 3 over 6. There we go. So that was right. FG up 6 over 3 gets us 2 over 1. So these are so far, not only are they proportional with the slopes, but we're also finding out that they have the same slopes. And then GE finally has 1, 2, 3, up 3 over 9, and that simplifies to 1/3 as well. So right here, we've got our corresponding points as well. So you can say angle A, angle B, and angle C are congruent to angles E, F, and G. And that is part of the answer that we are looking for, because we also need to write our proportional sides. You can check that by just using the slope as well, because you've used a similar triangle to set it up. It's kind of cool. Or you can use your vector form. So for example, with AB, it was 2, 1. And 2, negative 1, sorry. And then EF was 6, negative 3. And you can see that there is a scale factor happening there. From A, B, C to E, F, G, you can see that we're multiplying by 3. So we can also figure out that our scale factor is 3. And we can write our similarity statements of AB, BC, and CA being similar to E, F, G, move it on up, F, G, E. And if you'd like, you can also write out your extended proportion right here. So A, B, C, and then back to A. We've got E, F, G, back to E. So any one of these would work. Your problem was asking you for both this one and this one. All right, number 2, DEF has vertices, blah, blah, blah. What is the image of this? When you apply the composition. So what this is another way of writing the different transformations that can happen. So this is a dilation with a scale factor of 1.5. R over y-axis, you guys could probably figure that one out. And this is, in fact, the reflection over the y-axis. So we're going to set up our charts, DEF, with 2, 0, 1, 4, 4, 2. First, we're going to do that dilation, and that's going to get us D prime, E prime, and F prime. And all you're doing is multiplying by 1/2, 1.1 and 1/2. Another way to do that is by 3 over 2. Whichever works for you best, do it. And you should get the following points. If you want to use a calculator for this, by the way, you can. And then finally, we're going to get D double prime, E double prime, and F double prime by reflecting it over the y-axis. If you're reflecting it over the y-axis, then your y value is going to stay the same, but your x value is going to flip signs. So it's going to become -3, -1.5, -6, but your y values are going to stay the same. That's it.